day students. In this video lecture we will be seeing how to choose the initial centroids for the k-means algorithm. In the basic k-means algorithm which we have seen in the earlier lecture, we have seen that the centroids are selected randomly. But now the question is whether the random selection of the centroids or initialization of the centroids leads us to the proper convergence of the algorithm, or whether it gives the optimal clustering. That we need to discuss. That's why this topic of choosing initial centroids is taken over here. So when the random initialization of the centroids is used, earlier we have shown you a figure where the three natural clusters are present, and when you perform the 4 iterations, the centroids will move to the bottom of these respective clusters, and the algorithm will converge. In the same way, if you go to the figure 8.4, two things can be observed here. That is, one is the optimal clustering and suboptimal clustering. Optimal clustering means we are able to find the global minimum in such a way that a particular centroid is having a minimum distance from all these three clusters, so that a global minimum point is available to us. Here in the bth figure they have shown us suboptimal clustering, where you are going to have a minimum with respect to a particular cluster, but it is not a global minimum. So you can see over here, this particular figure, bth figure, is different from A. You are going to have some circle shaped points over here also, and square shaped points at the bottom. Why this has happened means this has happened because of the suboptimal clustering. That is, properly all the points have not moved to a particular centroids, and a optimal solution you have not got over here. This is because of the presence of the local minima or local minimum. It is minimum to a particular cluster, but it is not minimum when you are considering all the clusters together. So it is not well separated. That is why random initialization may lead to the suboptimal clustering. So choosing the proper initial centroids is the key step of the basic k-means procedure. A common approach is to choose initial centroids randomly, but it results in a poor clustering. That is what we want to avoid. So let us see it with an example. So randomly selected the initial centroids may be poor. The figures 8.3 which we have seen over here and 8.5 shows the cluster that results from the two particular choices of initial centroids. For both the figures, the positions of the cluster centroids in various iterations are indicated by the crosses. In figure 8.3, even though all initial centroids are from one natural cluster, the minimum SSE clustering is still found. Minimum SSE means minimum sum of square error clustering is still found, since it is having a natural clustering. Luckily or fortunately, it has happened over here. But in the figure 8.5, even though initial centroid seems to be better distributed, we obtain a suboptimal clustering with a higher squared error. If you see over here 8.5, if you see here in the iteration 1, we begin with the 3 initial centroids, then one particular centroids move to the bottom of the figure, but 2 of these centroids are still in the upper part. Means it is, even though we are performing the iterations, the centroids are not distributing in a proper way, so that we are getting the optimal clustering. Here the suboptimal clustering is happening, which clearly shows that the random selection of the initial centroids will lead to the poor clustering. So let us see the limitations of the random initialization. One technique that is commonly used to address the problem of choosing the initial centroids is to perform the multiple runs, each with a different set of randomly chosen initial centroids, then select the set of clusters with the minimum SSE. That is, for the first run, you choose a particular randomly selected centroids. For the second run, you choose another set of initial centroids. Like that, you do many runs. Out of these many runs, you select the clusters with the minimum sum of squared error. While this strategy may feel simple, but it may not work very well. The reason is it depends upon the data set and number of clusters sought. So we demonstrate this using the sample data set shown in the figure 8.6a. If you take this particular 8.6a figure, we are going to have the initial points like this. If we are going to perform the different runs on this particular figure or this particular data set, then how we are going to get the final centroids that at the end of the iteration, that we are going to see. See, the data consists of two pairs of clusters, where clusters in each top bottom pair are closer to each other than to the cluster in other pair. That means we are saying here this pair of clusters, this top bottom are closer to compared to the other pair of clusters to the right of it. So figure 8.6 from B to D show, if we start with the two initial centroids per pair of clusters, then even when both centroids are in a single cluster, centroids will redistribute themselves so that two true clusters are found. That means you can have we are having a pair of centroids for this pair of clusters. Then as we perform the iterations, it will redistribute. However, if we go to the figure 8.7, shows that if a pair of clusters has only one initial centroids and other pair has the three, then two of them will result in a true clusters. One true cluster will be split, means it will result in a suboptimal clustering. So if you see this particular thing, we are having a pair of clusters here and one centroid over here and one centroid for the pair of clusters. So as we perform the iterations, it will redistribute, and you may have two centroids here and one centroid here, but for this pair of cluster only one centroid you are going to have, which will ultimately lead to the splitting of this particular pair of clusters, which will not lead us to the optimal clustering. That is why taking the multiple runs with the different centroids or different initial centroids may not lead us to the optimal clustering always. It may give the suboptimal clustering. That is why that is not a very good approach for solving the problem of selection of the centroids. So let us now see some of the approaches to overcome the limits of random initialization. Because of the problems with using the randomly selected initial centroids, even the repeated runs may not overcome, which we have seen just now. Other techniques are often employed for initialization. What are those techniques? One effective approach is to take a sample of points, cluster them using the hierarchical clustering technique. What do you do means you take the sample of points, use the hierarchical clustering, and you obtain the K clusters. The K clusters are extracted from hierarchical clustering, and centroids of those clusters are used as the initial clusters. Instead of you going with the multiple runs of initial centroids, you use the hierarchical clustering, extract the clay clusters, then use the centroids of those k clusters, and you work on that. This approach often works well, but it is practical only if sample is relatively small, that is a few hundred of to a few thousand sample is there, and k is relatively small compared to the small size. If k is 5, 10, relatively small compared to the sample size, then this particular method of hierarchical clustering, extracting the k clusters, then using the initial centroids of those clusters is practically viable. Suppose your k value is too large compared to the sample size, it may not go well. Another procedure which can be followed for selecting the initial centroids is select the first point as at the random, or take the centroid of all the points. Then for each successive initial centroid, select the point that is farthest from any of the initial centroids already selected. Why we are doing this? In this way, we can ascertain that the set of initial centroids which we have selected is guaranteed to be not only randomly selected but also well separated. Suppose if you are having one initial point which is farthest to the another initial centroid, then we can ascertain that they are well separated, which will result in a well separated cluster. Unfortunately, such an approach can select the outliers rather than the points in dense regions, and also it is expensive to compute the farthest point from the current set of initial centroids. So that is the disadvantage. Advantage is you obtain the farthest cluster and well separated cluster. So these two approaches you can employ for the random to overcome the limitations of the random initialization. At last we will see what is the time and space complexity for your k-means algorithm. The space requirements of the k-means are very modest because only the data points and centroids are stored. Specifically, the storage required is the big O of m plus k into n, where m is the number of data points and n is the number of attributes and k is the number of clusters which we are going to form. So it will be m plus k, m data records or data points for k clusters into the n number of attributes. And time requirement for k-means are also modest. Basically it is linear. Since we are having the m points, we need to compute its distance and recompute the centroid and keep on doing this iteration until it converges. So the time required is big O of I, means the big I means the, or uppercase I means the number of iterations, k is the number of clusters, m is the number of data points, and n is the number of attributes. You may have 5 attributes, 10 attributes for each record. So your time required depends upon this one: number of iteration, number of clusters you are going to form, m into n, that is the m data records or data points into number of attributes for the each record. So I is often small and can be usually be safely bounded, as most changes typically occur in first few iterations. If you are having the many iterations, then your computations may be little bit high. Therefore, k-means is linear in m, the number of points, and is efficient as well as simple, provided that k, the number of clusters, is significantly less than m. So this is regarding the time and space complexity of your k-means algorithm. Earlier we have seen how to choose your initial centroid, how random initialization of the centroids will lead to the poor centroids, and how difficult it is in the computation. So you may use two approaches for overcoming the limitations of random initialization. So this is regarding the choosing the initial centroids for the k-means algorithm. So this brings us to end of this video lecture. In the further lectures we will see what are the additional issues related to the k-means algorithm. Thank you.